Okay, so our next speaker is STANISław from University of Toruń, and the title of his talk is Dynamics of Brief-Free Systems Generated by Behrend Sets. The floor is yours.
Thank you. Thank you very much. First of all, I would like to thank you for inviting me here and for giving an opportunity to give this talk, to present this this project. Thank you. And I also would like to congratulate to all the participants and winners and distinguished and Bank Prize competition. And I wish you many successes and a lot of joy with mathematics in future. So I would like to present some joint project with Mariusz Lemańczyk and our friend from Chile, Sebastian Zuniga-Alterman. And the whole work is dedicated to the memory of Professor Andrzej Szynce. So the title is Dynamics of B-Free Systems Generated by Behrend Sets. So first of all, I would like to, but how?
Green flame is paused. Probably I haven't completed. Excuse me.
Okay, I will start with explaining the setup. The first thing will be what is the B-free system. And how to change
The pages.
the pages.
I think that
With this present. Yes. Okay. But maybe I don't know how to use it. It's funny for a moment, but
it doesn't work.
yeah.
Trzeba włączyć. I have no idea how to turn this on. Słucham? Aha, żeby tego nie było. No teraz tak. Tak.
O.
Prawo, lewo. Tak.
Okay. So what we call B-free systems, a dynamical system which is defined by a set of natural numbers. One is excluded. The set is usually infinite. Finite case is not interesting. We also assume that this set, usually denoted by B, is primitive in the sense that two different elements from B do not divide one another. By MB, we denote the union of ideals generated by the elements of B. We call it the set of multiples of B. And it is easy to observe that considering only primitive sets B is not a restriction, because from the point of view of the set of multiples, it doesn't matter if you look at the set B, or you take just a maximal primitive subset. So without any restriction, you can think about primitive sets B. We are also interested in the complement of the set of multiples, the set FB, and the elements of the set we call B-free numbers. B-free is just not divisible by any element of B. Eta will stand for the characteristic sequence or characteristic function of the set of B-free numbers. And this is a 0-1 sequence indexed by integers. We also have the natural shift by 1 in the space of all 0-1 sequences, say to the right, for instance. And also we equip this set of 0-1 sequences with the natural, product topology induced from discrete topologies. in this set 0, 1. And now x eta will always stand for the closure of the s orbit of eta in this set, in this space 0, 1 up to z. By a B-free system, I mean the dynamical system in which the space is just x eta and the automorphism is induced by the shift denoted by s. This is B-free system, of course, it depends on the chosen set B. It's easy to observe that a sequence x, small x, belongs to x eta if and only if each finite blocks that appears in x appears also in eta. Block appears in x means just when you look at the finite piece of the sequence x, you just see this block. Block is a finite sequence of zeros and ones. So we know what is a B-free system. Together with B-free systems, it is convenient to consider so-called B-admissible systems. And to define it, let me first say what is a B-admissible set of integers. A set of integers is B-admissible if for every element of B, A misses at least one residue class modulo B. So this is here written in this way that A mod B is cardinal less than B for every B. It is easy to see that this set of B-free numbers is B-admissible because B-free number misses 0 residue class. They are not divisible by any B, so 0 is always missed. By XB, we denote the set of all B-admissible sequences, infinite in both directions. B-admissible sequence is a sequence whose support is B-admissible. Support, so I think it's clear. And B-admissible dynamical system consists of this space XB of B-admissible sequences and is also equipped with the shift automorphism S. It is clear that eta, I recall, this is the characteristic function of B-free numbers. Eta belongs to XB, as I said before, B-free numbers form a B-admissible set. It follows that this X eta is contained in XB. X eta, I recall, is the B-free system, the space of B-free system. In general, the spaces are different. There is no reason for them to be equal. And it would be very nice if they are equal. I mean, because admissible sequences are relatively easy to handle. And if X eta is equal XB, the situation is relatively easy and easier to understand. Let me give an example. Take for B the set of numbers consisting of with 4 and all primes. This P stands for prime. Do I have this pointer here?
The top button.
This P stands for the set of all primes, and we take the primes belonging to this arithmetical sequence. So this is the set. It's quite easy to observe that all numbers divisible by 4. This is clear, and all numbers in these sequences are contained in the set of multiples of B. And such a sequence is B admissible. This is quite elementary that it is B admissible. But thanks to this observation, it is also quite elementary that this sequence does not appear in eta, because there is no place for two neighboring ones in this positions here. It is not possible that such a configuration appears in eta because of this. I will not go into details, but I'd like to show you this example, quite simple example of a B-free system, which is different than the B-admissible system. A useful observation is the following, that if you have arbitrary set B, arbitrary primitive set B, then if something is P admissible, then it is B admissible. P stands for the set of primes. This is clear. And less clear, but not very difficult, is to observe that XB is always uncountable and has no isolated points. The first thing, the first observation that it is always uncountable follows from the observation that you can construct an infinite B-admissible set. And this is because you can construct an infinite P-admissible set. And the simplest construction is, I think, I don't know if it's simplest, but this is relatively simple construction. Just take, I think it is called primorial, the product of consecutive primes, 2 times 3, 2 times 3 times 5, and so on, so on. It's quite elementary to observe that this is a P-admissible set, and this is infinite. So each subset is also P-admissible, so you can observe that there are uncountably many P-admissible sequences. This statement about isolated points is a little more complicated, but it is not very. Okay. I think that consideration of B-admissible and B-free systems was motivated in particular by the example of so-called square free shift. So by this I mean the B-free shift in the case when B consists of the squares of primes. This was considered by Peter Sarnak in connection with his study on Möbius function. And in particular, he showed that in the square-free case, those two dynamical systems I defined, I mean the B-free system and the B-admissible, they coincide. And also he calculated the topological entropy of the system, and this topological entropy is this, which is not very surprising when you look at this, how B is defined. This observation that X eta is the same as XB allows to calculate the entropy. This is just the example in which you can better understand this B-free shift. How you can try to prove this equality? So first assumption you need is that B is infinite and pairwise coprime. I will tell you why, but let us make these assumptions. So B consists of pairwise coprime numbers. Now take a finite B-admissible block, finite. Thanks to that, thanks to pairwise coprimeness of the elements of B, you can find a finite subset of B, call it A, such that this block B appears in eta A. Now I'm interested in finite set A, and I look at the characteristic function of the multiples of A-free numbers. And it is easy to find such a set, to prove that it exists. And this is thanks to Chinese reminders theorem. Quite elementary. You can do it. But what next? This eta A is greater or equal than eta B coordinate-wise. That means if you have 0 at some position of eta A, then you have 0 at eta B. This is clear. It's easier to be A-free than B-free. So if the numbers in this interval, this is the interval in which you find the block B in eta A. If the numbers in this interval are free with respect to B minus A, then we found B at eta B, at eta B. This means that we constructed, we found the place in which B appears in eta A, and this place is not destroyed by the other elements of B. So we need some assumption which guarantees that this set of multiples, that the set of multiples of M beta minus A is sparse enough to not to spoil this interval, and it can be. We need to assume somehow that it can be made sparse enough by suitable choice of A. So I do not formulate this assumption now. I will come to this later. But you need something. Before that, let me show you two properties of B-free systems, which can be expressed in arithmetical terms and which will play some role later. First is proximality. As far as I know, a topological dynamical system is proximal if for any pair of elements of X, there is a sequence of natural numbers such that the distance between TQ and X and TQ and Y tends to 0 as n tends to infinity. So the orbits are closed along some subsequence of naturals. In the B-free setting, if we assume that X eta is proximal, we can apply this condition from the definition to X and the shift of X. And this condition yields that X must have constant blocks of arbitrary length. Just this proximality. But it is not possible that constant blocks of arbitrary length consist of ones, because we deal with B-free numbers, and it is so you take any element of B, so along an arithmetical progression with difference B, you meet zeros at this sequence. So those constant blocks cannot be ones, so they have to be zeros. So we have proved that x eta is proximal if and only if eta contains constant blocks of zeros of arbitrary length. And it is easily translated, you can easily translate it into arithmetical language. This condition is equivalent to say that B contains an infinite coprime, pairwise coprime set. And this observation is made in a paper by Aurelia Dymek, Joanna Kułaga, and Mariusz Lemańczyk, and in mine, in which we collected some properties of B-free systems. So proximality can be expressed in arithmetical terms, just as I showed. Next property is transitivity. And we can prove that for any B, now I'm speaking about admissibles. This admissible dynamical system X beta S is transitive if and only if B is pairwise coprime. The if part is relatively easy, but the only if part is rather complicated, combinatorially complicated, and I think it was a little bit surprising that this kind of theorem is true, but so it is. So, as X eta is always transitive, X eta is defined as a closure of an orbit, so it is always transitive. So, having this theorem, we can say that X eta can be equal XB if and only if B is pairwise coprime. So this is the only possibility. Now let me come back to the problem of proving how to prove that X eta equals XB. There's a theorem by Gerhard Keller that if B is taut, I will explain in a minute what does it mean, and contains an infinite pairwise coprime set, so this is equivalent to proximality, then X eta is hereditary. Hereditary means that if a sequence belongs to X eta, then each sequence which is coordinate-wise less than or equal also is contained in X eta. What does it mean taut? To define it, we need to recall the concept of density. And tautness means that every element of B is important from the point of view of density of the set of multiples. So when you remove any element from the set B, then the logarithmic density of the set of multiples decreases. Every element is needed to achieve this density. And one can prove that B is taut in the sense if and only if B does not contain any set, we say any scaled copy of a Behrend set. So B does not contain any set of the form C times A, where C is a natural number and A is so-called Behrend set. And the Behrend set is by the definition such that the natural density of the set of A-free numbers exists and is zero. So Behrend sets are such that most of integers are multiples of A, most in the sense of the natural density. So this is in a sense also an arithmetical condition to check tautness, and we have Keller's theorem giving a condition for heredity of the B-free system. And it has a consequence that if B is taut and pairwise coprime, then the B-free shift is the same as B admissible shift. So this tautness can be used as this mysterious assumption 2, which I mentioned before.
XB is always hereditary, right?
Admissible, yes. Admissible is always hereditary. This is clear. XB is always. So in a sense, thanks to Keller's theorem and to other results, the case of the top case is relatively well understood. And now our aim, the aim of the project I'm showing you, is to understand what can happen in the Behrend case. Because taut is something which does not contain any scaled copy of a Behrend set. Taut is relatively easy. So let us look at Behrend. Let me give you some basic examples of Behrend sets. First of all primes form obviously a Behrend set, because there are only two P-free numbers. It is -1 and 1. So the natural density is obviously 0 and P is Behrend, but it is not very interesting. More interesting is to observe that if you take any set of primes such that this infinite product is 0, then you have Behrend set. This is because this is just the expression for the natural density of B-free numbers in this case. Because, 1 minus 1 by P is the frequency of the numbers not divisible by P and by some kind of independence of the conditions. You have this, that the density of B-free numbers is just this. So for instance, you can take primes in some arithmetic progression, of course, in such progression which contains primes by Dirichlet theorem. In this case, this condition holds. Relatively easy, you can prove such a proposition that whenever you have two Behrend sets, then such a, product of this this set consisting of all elements of type BC, B is taken from B, C from C. This is also Behrend. This is not hard to prove. So, having this, we can say that so-called semi-prime numbers also form a Behrend set. A semi-prime are products of two primes. In this setting, we say that a square of a prime is also semi-prime. If you would exclude the squares of primes, it will be again Behrend. But okay, so these are basic examples of Behrend set. I showed you some characterizations of proximality of transitivity in arithmetical terms. Now I will show you some other way around, some dynamical characterization of the property of being Behrend. the characterization is the following. B is a Behrend set if and only if the B-free system is proximal and its topological entropy is zero. The topological entropy is, I think, something which you know, but I will recall this notion. First, let me say what is complexity of this dynamical system. By complexity, I mean the function associating to a number n the number of blocks of length n appearing in this dynamical system. And the topological entropy of this B-free system can be defined by as the limit of 1 by n of log of this complexity. So, okay. Few words about the proof. The proof from the left to right is, I think, is rather standard. Proximality is very easy. This condition on topological entropy follows from, I think, some classical inequalities. It's easy. But the other way around is not easy. It is complicated, and you have to collect several facts to prove this implication. So those facts are contained in the papers, in particular in the paper of Keller, Lemaitre, Ricard, and Sell. Of the title is Garden of Eden theorem, and in this Garden of Eden you can find arguments for this implication from the right to left. I will not go into the details of this proof, but the corollary from this observation is that the complexity of Behrend system must be sub-exponential, sub-exponential, because the topological entropy is zero. One of our results is that, in a sense, every sub-exponential complexity can be realized by a Behrend set. And moreover, this Behrend set realizing this complexity is such that B-free system is the same as B-admissible system, which seems to be difficult to achieve in the Behrend setting. So the theorem is that whenever you have a function rho satisfying such condition that rho by n tends to 0, then you can find a Behrend set consisting of primes such that the B-free shift coincides with the B-admissible shift and limit superior of complexity divided by 2 to the power rho n is at least 1. The construction, the idea of the construction is relatively easy. As you can guess, the construction is inductive, so you just construct finite subsets, and the set B you want at the end is the union of them. And it goes more or less like that. I will tell you about the step from the case to the k+1 stage. Assume that you have constructed BK. So BK is contained in some interval, say 1 to mk, and it contains primes. B0 is just singleton consisting of 1. And it is done in this way that every BK admissible block of length k appears already in this region, appears on eta BK in this region. Then you add you add nothing. In the long interval, you leave a lot of free place, and the length of this free space is large enough to satisfy such an inequality, and you require that every bk admissible block of length k plus 1 appears somewhere in this region. The blocks of length k you have already here. The blocks of length k plus 1 you have somewhere. And then you take consecutive primes, so many that this product is small enough. And this is this inductive step. The picture shows somehow the characteristic functions of this new bk plus 1. And when you take the union of those bk's, you can prove that B is Behrend thanks to this condition. Thanks to this, that those products are small enough, then you produce a lot of set of multiples of B. The density is small. And the complexity, the statement about complexity we derive because many blocks occur in these regions. So I think that the idea is relatively simple. Details are maybe complicated, but I think that the statement is a little bit surprising because Behrend's set seems to be very difficult to handle and to achieve that every B admissible occurs on X eta seemed to be difficult. And here we have such a construction. Okay, when should I stop? Because
you're way ahead of schedule.
So yes, I know, but
Well, take your time. I think
okay, yeah.
10 minutes.
No, yes, it will be enough. Let me now say some words about something we call the shift of primes, which is probably the most interesting thing. In the beginning, let me propose some convention, a simplifying notation. If you have a subset of natural numbers, then by x1a, I will mean x1 minus a union a. It means that when I have set of naturals, I construct some symmetrization of this characteristic function. I look at this as a two-sided. I have a characteristic function of A, and I look at the two-sided version of that. I think you understand. And the first observation is that when you have P2 free numbers, let me recall, P2 are semi-primes. So P2 consists of the elements P times Q. PQ are primes. P2 free numbers are just primes and 1, and the negatives of them. Nothing more. So when you look at the P2 free shift, then this is the dynamical system. This is the closure of the orbit of the characteristic function of primes together with 1. Of course, as in each B free case, this is contained in the set of P2 admissible sequences. But it is not equal. It is definitely not equal because P2 is not pairwise co-prime. We have proved that the equality equality holds only in the case of pairwise co-prime sets. So this is not equal. Moreover, it is, I say, unfortunately, it is not true that this is contained in the P-admissible system. But when you remove isolated points of this, the rest is contained here. Maybe I will comment it in this way. Why this is not contained here? Because you can take, for instance, numbers 2, 3, and 5, and 2, 3, and 5 is not 3 admissible because. Am I right? No. 2, 3, and 7 are not 3 admissible. 2, 3, and 7 are not 3 admissible. But if you look at the block appearing on primes, but a little bit far away, then it will be 3 admissible. If you take primes which are large enough, 3 primes which are large enough, they will not be not divisible by 3. Okay. Sorry. So this is more or less the reason for this inclusion. When you remove isolated points, you can forget about this one. So it doesn't matter if you start with the characteristic function of P plus 1 or without this one. This is the same, and this set is contained in the set of P-free sequences. If you assume one of famous and difficult number theoretical conjectures, namely Hardy-Littlewood K-tuple conjecture or Dixon's conjecture, then conjecturally this set is contained in X1P. So in simpler words, the conjecture asserts that every P-admissible block appears somewhere on this 1P. Every prime admissible constellation appears somewhere in the set of P. And but as far as I understand, the conjectures are considered as out of reach now. In particular, conditionally on the conjectures, this shift, the shift of primes is uncountable. If you know that it contains XP, you know that XP is uncountable, so this is clear. But this is conditional on the conjectures. And this was communicated to us by Professor Andrzej Szyńca. We discussed, Mariusz Lemańczyk discussed with him the problem of uncountability of the shift of primes, and he pointed out that it depends on the conjecture. It would follow from the conjecture. The Hardy-Littlewood conjecture is usually expressed, I think, in this way that whenever you take a p-admissible set of integers, then such a quantity behaves like x by log to the power kx. And this quantity measures the frequency of constellations of primes which look like this set sum with the positive constant c. Dixon's conjecture asserts more or less the same. This has some other features, but maybe I will not go into the details. Roughly speaking, both conjectures assert that every p-admissible block appears on the characteristic function of the primes. We have some consideration on the complexity of the systems we consider here, namely the complexity of the shift of primes is bounded from the above by such a quantity. The complexity of the admissible shift satisfies such inequalities, and assuming Hardy-Littlewood conjecture, we have also such approximation for the complexity of the shift of primes. The proof is in fact due to tau, and it is based on prime number theorem and methods of large C. This prime number theorem is used to use for the lower bound and large C for the upper bound. We tried to do something like that with respect to semi-primes, and we have the following result, that the complexity of the shift of semi-primes is bounded from the above by this quantity. And this is like n by log n, and here you have also log square log n. Conditionally on the Dixon's conjecture, you have also lower bound of this form. I will not go into details, of course, but this kind of results can be obtained with respect to this. But the most important, I think, inequalities are conditional on the conjectures. What can be done unconditional? This is, I think, the most interesting. Very recent result of Tau and Tamar-Ziegler is the following theorem. There exist, unconditional, there exist two infinite sets of natural numbers consisting of A1, A2, and B1, B2, and so on, such that the numbers AI plus BJ are prime whenever I is less than j. All these numbers are prime. There are such two sets. A beautiful result. And it is not a corollary, but it is kind of byproduct of their proof. For every infinite p-admissible set of natural numbers, you can find an infinite subset of A such that this A prime appears as a support of some sequence belonging here. So not every p-admissible appears as a support of a sequence here, but every admissible contains an infinite subset, which is a support of something really appearing. Thanks to that, you can prove, now it's easy, that the prime shift is uncounted. And this is unconditional. Okay, thank you very much.
Thank you very much. Can you wait a second? Maybe there are questions. Are there any questions? Yes.
This is the question from the Complete Live. You are describing the closure of the orbit. So these are the sets of sequences, but how many translation band measures are supported by these sets? These are not unique algorithms.
I think I'm not able to answer to this question. Sorry.
You mean the prime shift, right?
Whatever.
Whatever.
Yeah, these are nice, interesting sequences. Yes. From my point of view, we produce some interesting big infinite sequences. And so my question is, what are
the square tree?
The square
tree certainly supports many invariants.
Yes, but I
think it's hereditary.
But there are examples of unique algorithms, say.
I think the nature of things is that usually it's very many measures, but sincerely speaking, I cannot answer.
Are there conditions for the set B so that the B free shift is uniquely ergodic?
Well, I would have to look in this material. I cannot answer now.
The square free shift certainly has many because its topological entropy is positive, but the sequence itself generates the Mirsky measure, which is entropy 0. So you must have other measures than the Mirsky measure.
So I think in those hot and proximal, this will be the same. But well, I'm not sure.
May I have a question as well? You know anything about the isolated points of the prime shift?
Yes, we can say, but
are there any?
Yes. But for instance, the characteristic function of primes. It is an isolated part. Because, for instance, this 237 appears only
right.
This it appears only once.
Any other questions? Not, then let us speak. Thank you. Which of the recording? Stop recording.